Now, let us just start with understanding the basic structural steel, we can say, theory, and how we can proceed further in understanding and we can say becoming an expert structural steel engineer. So, first of all, the very first concept that we do need to understand is that when we're talking about the structural steel, we are basically dealing with either the bending application. That is, we do need to understand the bending behavior of the structural steel members. After that, the second, we can say, concept that we do need to understand is the shear. Third concept that we do need to understand is the compression. Fourth concept that we do need to understand, they are also known as the beam columns. And the fifth concept that we can understand is regarding the, we can say, composite behavior of structural steel members. And sixth and the very basic concept, that is basically the tension. So if we are talking about all of these, we can say, procedures. So AS4100, that has, we can say, different, we can say, sections to deal with all of these, we can say, different we can say behaviors of the structural steel, except for composite, that is basically covered in a separate structural steel code. That is, I think it was AS2327. So that code deals with the design of the composite section. So that we shall be discussing it at the end of this particular video lecture series. But most important concepts that we do need to understand for behavior of the structural steel is the bending, shear, tension, compression, and the beam column, or we can say that is basically the we can say mixing up of the bending plus, we can say, compression. So if we're talking about the bending theory itself, that is either we can say divided into either along the major axis or we can say along the minor axis. So shear is also, we can say, very simple calculation, and after that compression, beam columns, and we can say tension. So that is the first, we can say, concept that we do need to understand, that we shall be primarily dealing with all of these, we can say, forces, or we can say behavioral actions of the structural steel members. After that, we do need to understand that if we're talking about the structural steel, it is basically good in the tension. So in tension, structural steel is best, but in compression, concrete shows far better behavior as compared to the structural steel. So in compression, basically the compression capacity of the structural steel member, that is basically dependent on the lambda, or we can say slenderness ratio, or we can say radius of gyration also, that is R value. So that we shall be discussing in a separate, we can say, lecture of the compression members. But okay, so first of all, we have understood these are the actions that we shall be dealing with when we are talking about the structural steel members. After that, the second, we can say, understanding that we do need to have for, we can say, structural steel members is that we are basically dealing with the primarily two types of limit state. First is the limit state of strength, and second one is, we can say, limit state of serviceability. So if we are talking about the service state or limit state of strength, so in limit state of strength, we are basically much concerned about the strength of the structural steel member and the forces that are coming. So if we're talking about the limit state of strength, we shall be dealing with the factored load combination. So primarily we shall be talking about the factored load combinations, and for example, if it is approximately 1.2 times dead load plus 1.5 times live load, or we can say 1.35 times dead load. Or if you're talking about the seismic action also, or wind action also, then we shall be dealing with the factored load combination. And at the same time, when we are talking about the limit state of strength calculation as per AS4100, we add a factor phi. So phi value, that is basically, in most of the cases it is 0.9, or in some of the cases it is 0.8, or in some of the cases I think it is 0.7 also. So what exactly is this phi? So what happens is that, we can say primarily we do have two actions to deal with. first action is the load itself. Second action is the material, we can say consistency, or we can say material behavior. So what basically happens is that if we are dealing with the load, we have added the factors, that is we have added 1.35 times or 1.2 times dead load or 1.5 times the, we can say live load, or we can say imposed action or permanent action. But if we are dealing with the material behavior, it is not that in, we can say if we are, let us say if we are purchasing 2000 kg of structural steel, the whole batch shall show very exact similar, we can say values of the either yield strength or tensile strength or compression strength. It shall show some inconsistency also. So to deal with that, primarily it was first started in LRFD, that is load resistant factor design. That is a philosophy of the American standard, that is AISC 360. So what had happened, what basically this means, LRFD means load resistance factored design. So it means that basically the load is also factored, and the resistance, that is material, we can say strength also, that is also factored. So that is why it is known as LRFD. Alternatively, it is done as per ASD also, that is allowable test design also, which is not considered in AS4100. So primarily it deals with the limit state of strength only, and allowable stress design, or it is also known as the working stress philosophy. So that was the concept that had been, we can say, covered in the earlier, like 30 35 years back in the Australian standards. But in the recent Australian standard, it is not considered. So primarily, just to revise everything up, we have deal with bending, shear, compression, beam, we can say composite action or tension action in the structural steel members. After that, we do need to understand that primarily we do deal with the limit state of strength and limit state of serviceability. Third concept that we do need to understand is that we have to deal with an additional factor phi also. So this phi is obviously when is a factor which deals with the material behavior or material inconsistency. So that is why AS4100 has a separate table to tells us the value for the, we can say, capacity factor. So these are the capacity factors, and here you can see that so here you can see that for members subjected to bending, all of the factors are 0.9. So that is why it is a standard number. For members subjected to bending, we can simply take 0.9. For members subjected to axial compression, we can simply again take 0.9. For axial tension, again it is 0.9. So for members subjected to combined actions, it is again 0.9. And for, we can say, bolted connections, so for bolt and shear and tension, it is 0.8. And for bolt grouping, it is again 0.8, except for ply in bearing, it is 0.9. And for pin connection also, it is again, we can say, 0.8 for majority of the cases, except for ply in bearing, it is 0.9. And after that, for the, we can say, welded connection. So for welded connection, if we are proceeding with the complete penetration butt weld, it is, we can say, 0.9 and 0.6. And for, we can say, for longitudinal fillet weld in rectangular hollow section for thickness less than 3 mm, we are taking higher, we can say, factor of safety, it is 0.7. And after that, again, for plug or slot weld, weld group and other fillet weld and or incomplete penetration butt weld, we have to again 0.8 in SP category, and in GP category it is 0.6. So these are the, we can say, as we have discussed in the lecture few minutes back, that these are the capacity factors. So how we use that in our calculations? So that is also simple. Let us suppose we have this structural steel beam which is completely supported at both the ends. That is, the flange is completely supported. How it is supported? It may be supported with the help of, we can say, deck sheet also, and we have these stud also, and on top of that we do have concrete. So we can say that it is completely supported at the top. So now if the member is laterally supported, we do need to understand that it is the simple formula, irrespective of the country in which you are practicing. The simple formula for structural steel beam members is M equal to sigma into Z. Now Z is the section modulus, and we can say sigma is basically the stress, we can say, that is allowed in bending. So let us say in our case M is equal to sigma. So let us say we are talking about 300 grade of steel. So we are having 300 Newton per mm square or MPa. Thus we multiplied with Z, that is section modulus of any particular beam. So whatever value we are having, let us say we are having 20 kN meter, let us suppose. So this we do need to multiply it with 0.9 to find out the we can say limit state moment strength for this particular steel beam. So the value of the strength that we shall be having in our calculation shall not be 20, but it shall be 20 into 0.9, that is 18 kN meter. So if our load that is coming, let us say this particular steel beam that is having a UDL, and after calculating WL square by 8, this particular value is, let us say, 16 kN meter, and our capacity here is 18 kN meter. So we can say that in that particular case our section is safe because our capacity is greater than the load that is coming. Obviously this is the factored load, so we can say that, let us suppose, multiply it with 1.35, and after that we are getting this particular value. So obviously we are dealing with the factored load and factored, we can say, resistance itself. So with that we do need to understand that how we can apply these value of the capacity factors for strength limit state in the bending. So at the same time, if we are talking about this particular steel beam, we shall be discussing about the shear also, that is shear capacity. So shear capacity is also a very simple calculation, and it is again same for, we can say, either it is American standard or European standard or Australian or Indian standard, that we in majority of the country it is same, that whatever let us say this is the steel beam. So for shear, this particular web is the one that is acting. So whatever is the depth of this particular web, let us say it is 300 mm. So 300 into its thickness, let us say it is 6 mm, and again we have to multiply it with 0.6 for the shear strength, and again we have to multiply it with sigma, that is, let us say it is 300 Newton per mm square. So whatever value we are getting, this again needs to be multiplied with the load resistance factor for the shear, which is again 0.9. So here we can see that members axial, compression, tension, and web in shear. So for web in shear it is 0.9. So again, we can just simply multiply this value with 0.9 to find out the maximum factored shear that can come on the web. So as we had discussed in the earlier lecture, that basically the flanges are the one which resist the bending, and web is the one that resists the shear. That is why you must have seen in a very large depth plate girders, where the depth of the girder is very high, we do adopt the, we can say, thin web, but at the same time we add stiffeners so that our the capacity of the, we can say, girder, that can be increased in the shear also. And at the end we do provide end stiffeners, and in many cases, like if the depth is very high, we do adopt the, we can say, longitudinal stiffeners. So these are known as ILS, that is intermediate longitudinal stiffeners, and these are known as ITS, that is intermediate transverse stiffeners. So basically the philosophy, let me just explain it in simple words. Basically what happens is that we do assume that diagonal compression fields are formed in the plate girders if we adopt with this particular, we can say, philosophy. So these are the diagonal compression members for which we do need to calculate the area of this diagonal compression field, and on the basis of that we can calculate what is the maximum allowable shear that can come on this particular steel girder. So this is the philosophy that is adopted in many countries, and again we, for a very large depth plate girders, we have to calculate the capacity in bending. We do calculate by calculating the sectional modulus of this particular plate girder and multiplying it with sigma, that is the allowable steel stress. Shear we can simply calculate it if it is an unstiffened plate girder, then only plate web thickness shall come. But if it is stiffened plate girder, that is we may have added these kind of, we can say, stiffeners. So for that we do need to take the help of, we can say, diagonal compression field theory, or other theories also that are common when we're talking about these kind of girders. After that, we do need to check against the bearing action also. That is at this particular point where it is transferring the load, it should not get bent, or there is no bearing failure on that. So for that also, our AS4100 code is also giving us value about the web in bearing. So for again it is 0.9. So whatever value we are calculating, that we have to multiply it with 0.9. So bending, shear, and bearing. Torsion does not come here, and compression does not come here, except for these kind of small diagonal compression field stress. So that we shall be dealing in great detail when we're talking about these kind of behavior in the separate lectures. But just to give you a brief idea, that when we are dealing with the AS4100 2020 design of structural steel members, we shall be primarily discussing with dealing with either the bending, shear, compression, beam columns, or we can say tension behavior of the structural steel members. Now let me just tell you the easiest way to learn structural steel design. The easiest way to learn structural steel design is that we shall first of all start learning about the tension members, because that is the strength of the structural steel. So first of all, we shall be dealing with the tension only. After that, we shall be dealing with the bending members, the bending behavior. For bending, again, we shall be first of all learning about the bending of the supported structural steel members. Then we shall be discussing about the bending of the unsupported steel members. Then we shall be learning about the shear behavior. Then we shall be discussing about the compression, we can say, members or beam column members. So that is how we shall be proceeding with our lecture, or we can say video lecture series. So first, we shall start with learning with the tension behavior of the structural steel in the next lectures. So as I said, the point should be clear to you. What exactly are we doing? First of all, we shall be learning individually about the structural steel as an individual member itself. That is, if we are having an I-shaped section supported on pin support at both the end, this shall be the bending moment diagram. What exactly shall be the bending moment capacity, and how we can calculate that in ETABS and in manual calculations also. So experienced structural engineers can simply check the section modulus, Z value, or we can say R, radius of gyration, and then simply can calculate what exactly is the allowable bending moment capacity, or shear capacity, or axial compression capacity. So that is the level at which I do anticipate that you shall be going at the end of this lecture series. So steel is very easy. The only problem is that no one is going to tell you how to do it. So that is the intention of this course, that at the end of this lecture series you should be an expert in the structural steel design. So individual we shall learn, and after that we shall be discussing about the various types of structural steel building systems that are common in either in Australia or all across the world also. So I hope we shall be learning a lot in this particular lecture series. See you in the next lecture.